Welcome to finite element modeling. Today we'll be using Abaqus to solve mass diffusion analysis in composite materials. Today I'm inviting Fadhel Alsafar, who's going to help us go through this tutorial. Before we step into the tutorial, let me provide some theoretical background into diffusion problems, which is what today's Abaqus tutorial is about. In diffusion problem, Fick proposed the first fixed law and the second fixed law, and he demonstrated that the behavior of diffusion is similar to that of heat conduction. In mass diffusion, what you have is the mass flux is equal to the coefficient of diffusion times the gradient of the moisture concentration. And so that equation is critical in understanding the mass diffusion problem. The conservation of mass leads to the fact that the partial of the concentration with respect to time is equal to the gradient times the mass flux. If I were to substitute now the first law of diffusion, which is the equation that we're showing there, J equals the minus D times the gradient of C, and I plug that in to the equation of the mass conservation of mass, then I'm able to get an expression that's only in terms of concentration. So I have the partial of the concentration as a function of time, which is equal to the diffusion constant or the coefficient times the equation you see there. And what we need to do is now solve the concentration. A note of caution I want to point out is Fick's law accurately quantifies the concentration in many materials, but many polymeric materials do not show a Fickian behavior. It's non-Fickian basically. And so LF there plotted here is linear Fickian behavior, and what you see in the y-axis is the moisture accumulation, and the x-axis there is the square root of time, and the reference there below provides that. And you can see there curves A, B, D, C, and S are non-Fickian, while the curve LF is Fickian. So again, that's a note of caution, but today we're going to assume a Fickian behavior. So to develop the weak form, I'll start with a mass balance. And we see here that the integral over the volume of the material has the derivative of C, the concentration with respect to time, dV, plus the integral over the surface of the volume, n dot with the mass flux, ds equals 0. So basically, the concentration within the volume has to be equal at the mass flux to the mass flux at the surface. If I now apply the diversion theorem, or I found a way of integrating by parts, then I'm able to show the very second equation there, which is the integral over the volume dc dt plus the gradient of j dv equals 0. And because this equation is true for every d volume, then the integrand must be equal to 0. And that equation that you see there in the integrand is really now very similar to the equation we found earlier in the previous page. Our goal right now is to find an approximate solution for the concentration C. And that's an important aspect of the problem. We need to figure out how to do that. And this course, we learned several tactics, right? We were able to show that the equation there is the same as the one in the integrand, but we're able to show that I can use the weak form to Galerkin to approximate the solution to the concentration. So what I'm going to do, I'm going to multiply that by a trial function del phi. I could have a multiply by v or z or whatever variable, but here del phi is an arbitrary quantity. And that quantity is a function that I'm going to make orthogonal to the function, the differential equation I'm trying to solve. Again, the idea here is to approximate a solution for C, the concentration. So what I'm going to do is operate Delphi on this integrand, and that's not very difficult to do, just multiply it through, and you get the equation on the very right. What I want to do now is really come up with a weak form. So I need to integrate it by parts. And when I integrate parts, I'm able to put the problem into the weak form of the problem. So now what I want to do, I want to turn it to Fadhel so he can go through the Abaqus implementation. Now Fadhel is going to give a description initially of the importance of mass diffusion analysis, particularly the moisture diffusion analysis in composite materials, which is a very, very important consideration in the design of the structures, as moisture can decrease the capacity and the strength of composite materials. So understanding how moisture diffuses through composites is of great importance to us. So let's go over to Fadhel. Thank you, Fadhel, for your time. I appreciate it.
Welcome to this Abaqus tutorial. Today I will be talking about mass diffusion analysis in composite material. Composite has high potential to be used in multiple applications and adverse environments. And as a result of that, it's important to understand how it interacts with the environment. And part of it, how it interacts with the moisture. Moisture has adverse effects on the composites. It can weaken its mechanical and chemical properties. It can weaken the bonding that it has between the fiber and the strength. It can reduce its strength, especially when we have moisture at high temperature, as can be shown here. Its stiffness can be decreased a lot when it's subjected to high moisture at high temperatures. Its even glass transition temperature can reduce due to the moisture level. So understanding that is an important aspect of dealing with composites. And part of what we'll be doing today is to see how moisture diffuses inside composite material, which is something that is made available using final element and Abaqus. And once we deal with diffusion process, it's quite useful to make an analogy between heat transfer and diffusion process, since there are many similarities between them. For example, the temperature and heat transfer or thermal problem is quite analogous to the concentration and the mass diffusion. The thermal conductivity within the material and how fast the heat can transfer from one part of the material to another is very analogous to the diffusivity inside the material, in which how fast that the material, the moisture can diffuse from one part to another. The heat flux is analogous to mass flux in the material, and the general equation for the mass flux inside the material is described here, and which is what Abaqus uses here. Today, we'll be doing kind of three problems. One is 1D, and the other one is 1D with a paint or with a coating, and the third one will be doing it in 3D. Our problem today is described, at least the first one is described by this simple 2D diffusion problem, in which we simply have this plate, in which we'll be modeling it as shell element, and has this width, and is simply subjected to concentrations to concentration or saturation boundary conditions at the left end here. And the concentration is measured in terms of parts per million, in which its value, it's a value that we took from literature that at relative humidity, for example, of 95%, the equivalent moisture level is 17,000 parts per million. So what we want to do, we basically want to subject this material to a boundary condition of 17,000 parts per million here on the left, and see how fast it diffuses inside the material. The properties that we have is shown here on the left table, in which we have dx, dy, dz, in which the dy, dz will not be using them, at least for now. We use them for the 3D, but that dx, which is the diffusivity of the material, which is kind of analogous to the thermal conductivity for thermal problem, is described as such. And here it's described as at 2 temperatures, and you can see how large it changes from one temperature to another. And so what we'll be doing, we'll set these 2 parameters at two temperatures, and then we kind of in Abaqus want to see how the boundary conditions change as we change from here to here, and how fast that diffusion process will be. So let's start. This Abaqus will start as usual by setting our directory. And we'll start by naming our model. Okay, let's call it mass diffusion. Oops. 1D. And then we'll go to part and create, and let's call it mass again. It's a 2D problem. It's not necessarily. It's kind of 1D. So let's see. So we'll be using a shell element planar. And if we look at the size here, we have a size of 38.1 millimeters. So let's choose a value of 100 works. So 2D shell, approximate size. Okay, we're good. We choose a rectangle, 0, 0. And then we will use 38.1, and let's have a height of 30. The height is not going to play an impact on this here. So done. Now we'll set our material properties. Let's go to property, and let's call it composites. So the idea of our first problem is kind of to understand and to model the material and see its diffusion on 1D, and then try to move from 1D to a bit to more advanced problems. So we from here we need to go to other here, and the mass diffusion, and we need to create diffusivity. In the diffusivity, you can select isotropic, what we will be using now, and we have orthotropic, which we'll be using later. But for now, we'll use isotropic. We'll use the general model, and we'll have our property, which is 7.9, 7.9, E2 minus 5. And the concentration at the beginning will set it to 0. And this value will be changing later during the analysis. And we want to set kind of a trick now in which we say here it's at a temperature of 80. And now and here just to right click on this one and say insert row after. And now we'll insert the second property, which is this one here, 1.9 E2 -3, concentration of 0. And the temperature, we'll set it to 160, which is what we have here. And then we need to set another variable when we do mass diffusion problem, which is diffusivity. If we go back here to the equation that Abaqus used for the diffusion process, you can see here there is J, which is the mass flux, equal to S times D. D is the diffusivity, and this S is the solubility of the material, which means that how much can this moisture go inside this material and be absorbed by this material. That's how this measures. So for zero solubility, the material cannot actually diffuse inside. That's kind of what it says. So here in this process, we're trying to simulate the worst case condition in which we'll be setting this parameter to 1, in which we have 100% solubility or a value of 1. So that's what it says. 1. Okay. Now we'll create a section here. And let's call it section. We want to create a section now in which we will go to here and just call it section. And we'll choose a solid here, solid section. And you can set this one to 12.7 or as thickness, but anyway, it is not gonna have any effect in this, so we can set it to 1 here. So composites, and then if we go to here and click section assignment, create, and click on this one here, this is the section, and then done. Now we have our section here. Now we go to assembly. Within the assembly, we need to create the assembly, and then it's independent process. It's just like what we do usually. And we go to step then. Within the step, we need to create a step here, and let's call it mass diffusion step. And we need to choose mass diffusion here, this option here, and click continue. And you can see here within the diffusion process, it's kind of similar to what we did previously with the heat transfer. We have transient state and transient state, and we'll be doing a transient state here. One of the things that we need to understand about the diffusion process, especially if you look at the diffusivity here, it's millimeters square per hour. So diffusivity is a very long process in which it's measured in hundreds and maybe thousands of hours. So the total time we'll take like we'll take a total time of around here 2,880, and basically the reason behind using this is because of the literature that we're referring to, and so that we can compare the values that we obtain here to the literature. For the incrementation here, it is an important step. We need to increase the maximum number of increments that we'll be using because we have many steps. So that and these steps will take quite a while. So 100. If we choose 100, sorry, when Abaqus tries to solve, it will take this the solution into increments, and for that, this large number, it will take most possibly it will take way more than 100 number of increments. So we'll use this one up to, let's say, 4,000 here. For the initial step, let's use quite small initial step. And for the largest step here, let's use it as 5. There is an important step here to take into consideration when doing this here, especially when using the time increment size. And here to explain it, let me go to Abaqus website, or not Abaqus website, but a website where you can find a lot of things about mass diffusion process, or Abaqus in general. Just when you Google mass diffusion analysis, you'll be directed to this page here, in which it speaks about the functional used for in this analysis, the governing equation, which each parameters use, the units that are using, which all these are important and useful to understand. But here, what I want to go over is the delta t, which is kind of the minimum delta t, the time step that we want to take. And here they're stating it as this step has to be greater than 1/6 times d, which is the diffusivity, multiplied by delta L squared, where delta L is the length of the side of the element that you're using. If your delta T chosen is smaller than this, then there is a possibility that your solution will not converge. In our case, since we're using 2 diffusivity, you can take its average, and you'll find that we'll have a value within the acceptable range. If your value is below that one, it's not necessarily that it will not work, but it may not converge. So just based on that, I just remember that I need to have a kind of a maximum step size of around 20. So I don't want to make it very small, otherwise I'll have that issue and my solution will take a while. So, and here I have to set this step, which is just like what we had with the thermal problems, and what we're setting the maximum temperature change per increment. And here I'll have the maximum change of 20. Remember again, I just want to reconfirm that the boundary condition that we'll be setting, which is coming in the next step, is measured in 17,000 parts per million. So if you choose here a value of change of, for example, 0.1 or 0.5 or even 1, that process will be very slow, and it will take a while. So by this one, I believe we're done. Okay, let's go to load now, and we want to set the boundary conditions. Let's call it concentration boundary conditions. And here we should go other, and since here it's mass diffusion process, it's go to other directly, and we should choose mass concentration here. And we want to choose this line here and click done, and then just go to magnitude. And here there's one thing that we want to do. We can either set the boundary conditions to 17,000 parts per million right away, or we can have it kind of changing with time, and have this value changing with time on this boundary, and then it will start to diffuse inside. And that's what we'll be doing in this. So just as if the concentration here is first start with small value and then start to increase. I mean, within here, and then it will start to diffuse inside. So we'll be doing this with the boundary conditions. So we'll have kind of variable boundary condition. So that's good. So it's really good to learn that. And we will see later how we apply variable, how we change the material properties, which is the diffusivity in this case, in the middle of the process. the middle of the step. So here, what we'll do is let's close this one here, and let's go to on the left side here. We should go to amplitude. Yeah, go to here, amplitudes here. Double click on this, and let's call it variable and click on tabular, and now we'll see what we do. So we make it kind of variable to change the property to change linearly. And here we have a table in which if we insert values, it will kind of interpolate in between and just draw it if we have distant points. So enter this one as this and this. You'll see now what I mean. And here what we have at the last step, which I set it to 2,800. So I have a 17,000. So let's frequency here, it's time or frequency, which is the time step that we chose. So what we have here, I want this value to change up to 2,000, and by 2,000 I want this value to reach 17,000. To understand what I mean here, let me show you this here to understand what we did. If you go to on the top here and you go to plugins here and you click on that and then you go to tools, you see here amplitude player. If you click on that and you'll see this is what we created. If you click on plot, you'll see that within Abaqus it created this. I just entered two points, and it's basically it creates a linear line between them. And basically this line, this changing properties will be applying it as a boundary conditions. So create again boundary conditions. Concentration. And we'll choose again this line here, click enter, and we'll be here amplitude. If you click on that, now you'll see the value that we set. Choose it, and for the magnitude, choose it as 1. So basically this magnitude will be multiplied by this value here. So we want it to be 1 so that we have values inside this table or this changing property. To have the material changing during the analysis, to change the diffusivity, we go to predefined field here. So we'll create, let me call it temperature field. And there's only one option here, so choose it and choose the whole field here. And click OK. And within this here, we want to create an amplitude. And to do it, we can go back, just like we did to the amplitude and click, or click here right away. So create amplitude. So let me call it temperature field. And let's choose tabular again and click continue. So at frequency 0, I want the amplitude now, which is the temperature, I want it to be 80. Now let me kind of recall. When we set our material property, we set our material to be temperature dependent, and we set the temperature to 80. So that's what we are doing now. We were saying that now it's the temperature 80. We kind of telling Abaqus relate that 80 to this value here. And now the time frequency, we're saying our value up to 2880, and this one here up to 160. So what will Abaqus do now it will kind of, let me go back to here. It will kind of create a line that will change this diffusivity from here to here linearly as the temperature changes from here to here. And the temperature is not actually changing. It's kind of, we set a range and we tell Abaqus, okay, this consider as 80, now change the material property. This is kind of what we do. So let's click on that and click again this to 1 on the amplitude temperature field. And then section. All right, and now we are done with this step. Let's go to mesh and design. Let's make it structured, quadratical structured. And here, since we have diffusion only along this direction, having mesh into along the y actually does not help, because I'm only interested in the x direction and this problem. So I will choose this option here, and we'll choose this line to create mesh along that line. And let's have it 1 millimeter. So let's see if we can have 0.5. Possibly we'll have some issues, but let's check. Yeah, but it's an error. Let me raise this one here. So basically, I do not want elements along the y, so that will take time, and that's not helping me actually. So that's I'll click on this again. I'll choose this here, and we'll say I only want one element along this line. And now let's see. Just that it seems that we need to make these a bit larger here. So this is the one. So yeah, you can see along the y we have one element, and here along the x we have these elements here, and then we need to set the element type. And within here we will choose heat transfer. So heat transfer, and we'll click OK. And by now I think we're almost done from the first part. Let's create the job, and let's call it the same name as Fusion 1D. Click. Okay, let's hope that we haven't made any mistake. And let's do that data check first. And perfect, it's done. And probably we can submit it now. Come on. Come on. Okay, submit. And let's monitor it. And it's good to see it now, because you'll see now for the diffusion process, it involves quite many steps, and it's good to see what's happening within these steps. So let's decrease this one here. No, that was fast. Probably I should have made the step a bit smaller. So you can see that the total time now is around 500. And if you recall, I said the predefined field, the temperature, to change at step of, I believe, 500 or so. So at 500, you can see that the material will start to change, or at least the step size, because the change of the material property. Oops, didn't. All right. So we're almost there. So let's go back to the slides as that's running. Let's kind of discuss what we want to do. So basically, we want to run this diffusion problem, and once we're done with that, we want to see the effect of adding a paint layer or a coating layer for the composite to protect it from the moisture. We want to see how that helps in protecting the composite from the moisture. And once we're done with that, we want to go to 3D and run the model in 3D, in which we have diffusivity along the X, Y, and Z, which means that the diffusivity along each axis is different, and the diffusion speed will be different. So we want to run all these 3 cases and see our results. This is for the comparison. We'll come to it later. So now it's done. Let's go to results, and let's see our results here. And just to make it a bit more clear, we can go to Viewport annotation. If you go to legend, set fonts, I can actually make this this color bar here to make it a bit larger here so that it's more visible. So apply. All right. And if I don't want this white box, I can as well change it here. So show now. So you can make it like this. Let's try to move this here a bit. Now we kind of see the diffusion process. We can run it and see immediately. We're clicking on this one here, and now we see how the diffusion process goes here. And the beginning it's quite slow when the material properties start to change, and we have faster diffusivity. You'll see that the diffusivity will start to speed up the more that the concentration increase here at the beginning. Okay, cool. Let's okay, that's enough. So let's plot the data and see how it looks like, and see if you want to compare it. If you go to path here, create, and let's call it path 1D, and I'm going to choose the points here on the top. Possibly for this one, if you want to have denser mesh, we need to divide the structure and either in the assembly or in the part step. So that would help to make to have more elements. Possibly that's what I believe. Let's choose this. Let's move a bit here. Okay, and I think we're done. Let's choose more. I'm almost there. Then, and okay, if we go to XY now and go to path, I want to see the plot, and I want to see it along the x-axis. And here we can see how the plots look like, and possibly we need a bit more mesh or so. But we go back to what I have here, and wait, this is a bit larger, so if we make it up to 25. So if you click on this here, you can say here, you can choose the axis and say up to 25 and click enter so that you can see a bit. And you can make the axis larger a bit as well. So yeah, here. Cool. You can change it here. Depth. And that axis is the concentration in terms of part per million. And let's make it a bit larger as well. So if we want to compare the results, which is something that I've done before here, and see these results and the diffusion as it moves from the left edge, which is at value here. We can add some points here to see it's 17. It's just like what we said here. We can have a bit more ticks here, some by increments. Oops, by count. So if we do this, I believe yeah, here's the 17. So that's what we said, a value of 17 E3 from the slides here. Oops. Yeah, that's what we said, and that's what we see here. So, and we're comparing our results here with the results from the literature, and we're increasing the number of elements. And we have a plot in which it shows how it changes from value of 0, which is this the left edge, and from concentration of 17,000 part per million, and it reaches up to to this value, which at 10 starts it decreases to around 0, and there's nothing here. If we add more time, more diffusion time, it will start to diffuse more. So that's kind of we are setting our material to adverse conditions. We set the boundary conditions to high concentration. We make the material to be 100% soluble, and we want to see under this adverse conditions how the material behave, how fast that diffusion process inside that material is. So that's kind of the idea, and the results between it and between the literature, they're quite small. There are some differences, and it depends on the way that you set your boundary conditions or so. But that's the way that we did it here. If we look at the profile here, if we go to here and compare what we have here with what they have here for the plot, again, it's quite similar, and the values probably may need some more mesh in there, but that's the idea, and that's what we have here. Okay, cool. That's good. And by this, we kind of finished now our first part, and we can move to our second part, which is very similar to this part, but with we'll add one more layer. So let's do it, and we'll do it in a bit different way. We'll learn a bit something more as well during this step. So let's go to model. Let's create a new model here. Model, create, and let's call it mass diffusion 1D with coating. And let's say, okay. And now this is our new model, but it has no part. You can either start from the beginning and create your part, which is fine, or we can do this. We can go to model here, copy objects, since we'll be using same model here, and we can go to here and click into part, in which it will copy the part. We can copy the instance as well. We can copy the material property. We can copy the section as well. So that's interesting. And let's copy the amplitudes. So we're copying kind of everything now. So let's click OK. And now if we go to here, okay, this is mass diffusion, all right. And let's choose this one. This is our model. And here's our property. So that's good. But we want to do one thing here. So as we said, we want to have a coating layer that simulate a protective layer, and we can do it this way here. And oops, so that's face. And let's use a sketch here. We want to divide this structure into small part here, and which that small part will resemble the coating. And the coating here, we within this problem, I'm saying it around 200 micrometer, which is 0.2 millimeter. So let's go to here, line, and let's draw a line, a vertical line here. That's what the way. Oops. That's a vertical line, and let's go to here at the dimension. I want to set the dimension from here to here, and this dimension I want it to be 0.2 millimeter. So remember, our dimensions are in millimeter, so that's 0.2. And let's click OK. And let's click done here. Let's go to property. Since now this is a material with probably will be with different. It's a coating material. We want a material with low diffusivity, and that's what we will be doing. And let's close this one. Close this. So and I want to go to the material here. Since it's set now, the material property and the section is set to everything, and I do not want that. I want to set it to have different material and different properties. So let's click on edit here. Let's go to pick. I want to choose only this part, not this small one. So this one now is not chosen. I only want to choose this one, and click done here. And click OK. So now you can see now this is green. This is not a green. So we want to make it a green, but green with different material property. So let's call it now coating material. And again, the problem is the same. It's a diffusion problem. So we want diffusivity and we want solubility. So now let's, for example, let's see that it's not 100% soluble. We want to find a good a good coating material. Let's say that it has. Honestly, I'm not sure. So let's go to 0.8 solubility, or maybe 0.7 solubility, and let's have a value of similar to the initial value of this one here, and let's assume that it will sustain this this protection layer here. So we'll have this value here as our diffusivity for our coating material. So let's have 7.9 e to -5, concentration of 0, and solubility 0.7. And let's go to and let's click OK. We need to create a second section for the second material. So let's call coating material, again solid. OK. And let's choose our coating material. And now we need to assign it, create, select this one here, and we want to select our coatings material. And it's a green, so we're good to go. Perfect. Let's go to assembly, and it's a bit angry now, but all it says that failed to attach mesh to the geometry. It just means that we need to remesh again since we created this small part. Other than that, all good. And let's go to a step. For the step, we are not changing anything. Same step. Oh, we couldn't import the step, so we need to create the step. Yes. Mass diffusion. Step. Answer. And we'll have same time as before so that we can compare it. And it's let's make this one's this one here. Let's say that's 20. This one to 4,000. And last time was quite fast. So let's reduce this one to 15 here. And let's click OK. And now let's go to load. We'll do the same step as the last one. And now the load, the mass concentration will be applied now to the coating material, not the not the layer, not the composite right away. So let's choose this one here, which is the first phase or first phase of that coating material. Click done, and we want to use same variable concentration so that we can compare it, and that's 1. And for the predefined field, we'll use exactly same thing here. I believe let's call it temperature field. And click OK. And for this one here, I selected it's for this. Click done. And it's only for that one, that material. It's not temperature dependent. So select this to 1 and call it temperature field. And OK. Perfect. So let me just recheck. Okay, plugin tools. So yeah, you can see I can plot the variable and the temperature. If I plot this one. Okay. And now we can go to mesh. And let's have a structured quadrilateral mesh. Let's have, okay, same size. And let's see if we can have. And oops, no. So again, I do not want anything in there. Same here. I do not want anything along the y-axis. That's just consuming memory and it's not helping. So, and okay, I think we're good now, hopefully. Yes. And let's take a look. All right, perfect. And now let's make sure that we have the right element for everything. We want to hide the transfer elements, and you can try the quadratic element, but for now I'll use this one here and we'll run it. And let's hope that we haven't make anything wrong. Let's create a new job and let's call it mass diffusion 1D with coding. And okay, submit. So we want to see how that coding material helps and in reducing the diffusion process in here. So that kind of help with the design process if you want to reduce the diffusion. And then once we're done with that, we want to move to the 3D problem. Okay. Let's monitor it and make sure that everything is going fine. So let's see. It looks nice. That's it. It's a bit taking more time this time. I reduced the increment step from 20 to 15 for the minimum change, so that can have an effect as well. So you can see here now it's reached 1,000. We're supposed to reach to 2,000. So I'll pause it to save time and see you in a bit. So you can see that this process is taking a while. And so during the analysis, possibly it's wise that not to have a very fine step, I mean increment size. Otherwise, your analysis won't be done, and you'll run through a lot of troubles. So yeah, it's good to kind of test with this increment size thing. And it's done now. Let's go to the results. And let's see. And things looks cool. Let's move this one here. It looks a lot different than the previous one, and it seems that coding layer that I added, that it has to be realistic, but that value is kind of what we have from that composites. So it might be not so far. So let's plot the results and see. So previously, just to remind you, it's so that we can compare something in terms of that, how things looks like. It's not here. Yeah, so we had something like this here, and now we have this, and let's see if we can go to here. Okay, just a second. So yes, if you actually go to here and click create, you can create a new viewport window. So you do this, and then click on this cascade, which it will show the two windows, and you can click on here so that you see them. And now let's in there I have the brief the current results here, which is this one here. So let's click on this window, and on the left here, I have my previous run or previous simulation results, which is this one here. Let me double click on that and do this, and now I can see them against each other, and I can compare. So you can see that it's quite a large difference, even in terms of the maximum amplitude. And here the maximum amplitude, that's quite good to know. The maximum amplitude is smaller now because of one reason, because the solubility of of that coating material was not 1. And on the one on the right, we set the solubility to 1, and with that one we reached our maximum concentration on the edges, which we said our worst case scenario. On the left hand side, we added the coating, and we assumed that the coating has a solubility that less than 1, which has a 70%. And you can see here, even though I set the same concentration level of 17,000 parts per million, I haven't reached that value. Let's plot the results and see now. Let's go to path. I believe I can use, yeah, I can do this here and plot the results on the left hand side. And I can go to this window, and I think we're using the same data. It's a smart. No, it's not that smart. I need to create a new path. Anyway, yeah. Let's go to path, create path 2. Let's call it, yeah, path 2. I don't have any nice name. Path 2 with coding, and let's say continue. After, let's zoom in here. Let's choose these points, and oops, no, I need to move it. All right, so this one, this one, this one. Let's have a little bit large picture. Oops, that's crazy. Move it down. Almost done. And that's good enough. And okay, now we can go to the XY data path, continue with coding plot. And I can now compare the two plots and see here. So you can see here this plot here, it's up to 5, and how large, a bit large this distance is. And for that one, you can see I have it quite narrow in there, while for that one it's quite wide, and that's kind of the effect of the coding that's playing in there. And yeah, so that's it seems that that coding is effective. It's kind of shown in there. So it seems that there is a quite a bit sharp edges in there, but it's probably with more mesh here, this can be more smooth, but I believe we can see the effect now. Okay, that's good. Let's go to here. Let's go to here. Oops. Nope, not this one. So we can again do this. Yeah. So again, that's what we have. That's the effect of our coding here. We have a coding material with a solubility that's less than 0.7. We saw the effect of solubility, and we now kind of we can compare these two. With this, we concluded the 1D or 2D part, and now we can move to the 3D part. Cool. Let's start with the 3D part, and let's go back to our model here. We can close one of these windows and maximize the other, and then go to part here. And let's create a new model here. Create mass 3D. Let's finish it fast and go home. Okay, almost done. And mass 3D. I want to do 3D solid. Okay, 100, that's fine. Formable, done. Let's go to our 3D part. So for the 3D part, we have same material properties, but now we have diffusivity along X, Y, and Z. We have the two temperatures. We have the size of this one, which we have the width of 38.1 along the X, and along the Z we have a depth of 12.7. We have a height of 38.1. So let's set these parameters now. And we have extrusion here, so we will set the rectangle 0, 0, and this one should be 38.1, and the height should be 38.1, and then the extrusion now it should be 12.7, half an inch, I guess. And okay. So here in 3D now, we move to the property, we set the material property, and let's call it composites 3D. So let's go back to here and let's understand a bit better and what that means. So basically, usually with composites, you probably have will have the lamina, and the lamina is will assign a stack, and that will make the laminate. And within the lamina, is supposed to have the direction of the fiber. But in terms of diffusion, for each direction, it's either that you have along the diffusion along the direction of the fiber, or diffusion along the depth, or diffusion along the sheet, or the thickness of that material. So dx here is kind of the diffusion along the direction of the fiber, and dz is direction along that depth here, and dy is this one here. So let's go here and let's set these parameters: mass diffusion, solubility, mass diffusion. Oh, that's diffusivity. This is the solubility. So again, worst case of having one in there, and here we will make it temperature dependent. We want it to be orthotropic this time, so that's now we're doing a 3D and it's composites, and diffusivity, as stated, it depends on that location, so, or on the orientation. So this is 7.9, not 5, e to negative 5, and that's 7.43 e to minus 5, and 5.34, 5.34 e to minus 5, and that's 80. We can click enter and we'll go to the second line with 1.9 e to minus 3, and 1.77 e to minus 3, 1.15 e to minus 3, and that's 160. All right, and now, so now we're almost done with the material property. Just we need to create a section. Let's call it solid. Let's call it composite. Here it's kind of like kind of bizarre. We're calling composite, but we're using a solid, and part of it's that it's the diffusion process that's depending on the direction. But other than that, the section is solid and homogeneous, and that's controlled by the material property. And we'll add something that probably would make a bit more sense now. So let's go to create section, and this one here. And that thing that probably should make a bit more sense is that we need to go to here, and it's an integral process when we use orthotropic material, where the orientation and the composite is kind of coming as assigned material orientation. And now we need to select this one here and choose that one. Now here we can see here, this is the direction of, supposed to be the direction of the fiber, and that one is the thickness and y. But we just want to make sure that this one is along this direction now. And it's believe we're good to go. Okay. And it should go to assembly. independent. Okay, and step. Let's call it plus diffusion, step, mass diffusion. Okay, and let's do just like the last time probably. But this one will be a bit long, so let's make it a bit shorter now. We know that works. So that's kind of 1,500 hours. For this one, let's have it 3,000 maybe. It's one. It's 20. 10. Okay, then okay. Let's go to load. And now for the load, we can either now run the model and apply the load into various directions and mesh it and wait for the solution, which will probably take some time, or at least for the purpose of this tutorial, apply the load or boundary conditions at one direction and mesh it along that direction, and then measure the diffusivity along each direction separately, which probably might be a bit faster. But if you want later to see all the effects of all the loads and boundary conditions, you can apply the loads to various directions here and there and mesh it completely and run it. Let's call it diffusion along Y, and let's set it to here, and so it's good. Now we can recreate the amplitude, though we can't call it from the last one, but let's call it concentration, boundary conditions, amplitude, and just like what we did last time, 0, and start at 0, 0, and here it's 1,700. Okay, let's set this to 1, amplitude this one here, so we have it here, and let's set our predefined field. Let's call it temperature, and again, we're not doing, literally, we're not doing thermal analysis here. It's called temperature, but what we're doing here, we're assuming that here at this field the temperature changed, so change the material properties, but there's no heat going on here or the thermal analysis that's happening. And for this one, let's create the temperature field, just like the previous one. So starting from 0, that's A, and the 500, that now we're reaching 160, and the material property is changing in between. Let's apply this one here, done. And let's go to mesh. And what I mean now, we apply the load here on the top, and you want to see the diffusion along this direction. So I can either mesh everything, which will be something that's quite huge, or I can mesh it along this direction here and apply, for example, here. Let's it's out here, 1 millimeter here, and here and there we can have of one element and mesh it. Oops. So probably we need to do this. Okay, and here, probably here as well. Set it to 1. So I just selected this edge and that edge and that edge and selected the number of elements or the C's on these two to be 1, so that when I run this one, I only have elements along this direction here. Let's set the element type, and I want it to be heat transfer. And here it is, heat transfer. And that is the element that's used here. And okay, I think we're done now. So let's create a job. Let's call it mass Fusion 3D. Done. And let's submit it. And let's see. Some warnings. Probably that's fine. That's not gonna hurt. So you can see that's quite fast. So we're already at 900 something. Let me pause it a second. I got that it's done here, and it took 500 increments. If we reduce the change per increment, then most probably this number will increase. So let's go to results, and let's see. So that's how. Let's click on this one. Yeah. So that looks a bit better. And let's see the diffusion along that line. Let's create a path. Long. Let's go path along Y. Now done. And let's zoom in here. Select these. And I think that's enough. And done. And okay. Let's plot it and see. Right. Let's plot. This is a plot that we just created. Yeah, it's this one here, and we need to choose this one here. It's not a long wire. We need to use this one, or either you can use the true distance. This one here. So you can see here that's the diffusion. From last time it was up to 5 here, but now along the y direction it's clear that the diffusion is slower, at least, and now the time is smaller as well. And we can do the same thing along the x-axis, which is along the fiber direction, and along the depth as well. Let's do that. Let's go to let's go back to here and go to mesh. Let me remesh. Let me delete all the mesh first, and I'll delete everything here. So just to click, hold, and you can do this. Select all, enter, and now all the seeds that we did before are deleted. So, and we can go here. Now we can, for example, see the diffusion along this direction. And to do so, we can choose this one here. And we can choose number, the element size up to 1. Yeah, that's good enough. And other directions, I just want to set them to 1 element. And let's see if that's, I still need to probably here. Let's set this one to 1 element. And on it, you need to do a bit more. So it seems that I just need to select, to make sure that it's not necessary, but just to save computational time. So if you want, you don't have to do this. Oops. Okay, delete and enter. Okay, I'll live with this. I just, if I want that, I can delete those or set this one to 1. But for now, and I wanted to go to load and change the load from that surface to, now I want to select this surface and see it along this one here. So let me call it diffusion along z-axis, and it's this one here, and similar to that one, and I will use same condition. And for the previous one that I said, I will suppress it. So which is this one here. So all what you need to do, just go to here, click on this, and once you see that this red cross, now it means that it's not applied. So yes, and go to job. We can create a job to compare them. You can copy this one and say along Z, submit. The analysis is done now, and let's go to results, and oops, let's go to here. Now it just shows it's showing what we had before. So let's do this. Now we have the diffusion that's coming from this direction. It's going inside here. So let's see it this way here, and let's plot it and try it and see. So let's create a path. Tool, path, create. Let's say call it path along. Now it's along the axis. Let's zoom in here. Possibly we need finer mesh here. Done. Okay. And we created that. Let's go to XY data path. And that's the previous path, but we want this one here. And just do not forget to change this one. And now let's say plot. And you can see here this diffusion is slower. And if we go back to the material properties, you can see the diffusion along the Z is slower than the diffusion along the x-axis, which is what we not slower than the y-axis, but the one we did before is the y-axis. And we can see, we can have the two plots that's just like this. Okay. And let's have this one here. That's what we did last time. And we can get our plot for that one. Oops. Oh, we still have this one, we can use it. Once we highlighted that window, so we can do this. And want it along the y-axis plot. And you can see here, it's here, this one here, it switches up to like 5, and this one is up to 4. So you can see this one has diffused farther into along the y-axis than this one had along the z-axis. And probably you can later extract this data and plot them against each other and see. But yeah, you can see now how these data varies. And probably we can add more more points here. That helps a bit with the comparison. Okay, this one here, 20. And let's see if we can do this the same here. Oops. Click. Oops. Highlight this one first and then double click. And done. Oops, this one looks more crazy. Yeah, but yeah, we can tell here that this one stopped like earlier than last one. And if we plot them against each other, we can see that. And what we can guess as well for the x-axis, that for that one, since it has higher diffusivity along that axis, will have faster diffusivity as well than the x and y and z. And with that, I kind of conclude what I'm planning to do for this tutorial. So again, I'll try to reiterate what we did. So let's go back. We basically want to see how the fusion process along the thickness of the material happens, and we plot the results. We're using variable using variable concentration, which the concentration on the edge was increasing linearly here, and then it started to diffuse inside the material. And versus that step, we assume that the temperature is kind of changing within that environment, and we adding that effect of temperature change, which is changing a change in the diffusivity of that material. And that diffusivity is accounted by this value. So we entered this value and we added a temperature dependent step. And then we added another step as a predefined. And due to that, Abaqus was kind of will kind of create a plot between these two results, which is this one and here and this one, and will continuously change the diffusivity parameter of the material and give you the results based on that. We did it in 1D. It's called, actually, it's 2D, it's not 1D. We did it in 2D, and we added a coating layer with smaller solubility, and we saw that using smaller solubility, even though we applied 17,000 parts per million, the resulted concentration on that layer was smaller, and that's because its solubility is smaller. It cannot take more than that, and that's the meaning of solubility. We learned that, and then we went to 3D. We modeled this. We modeled the material as orthotropic material. We added that, and we saw how we set the material orientation as well. That helped that, and then we applied same boundary conditions, same everything, and saw that how the material property changing along Y, Z, and X. What you can do later is actually to mesh whole material along the X and Y and Z and apply diffusion from different direction and see how that happens. The combination of all these concentration parameters that happens on the edges. I hope that was useful, and thank you for following this, and thanks.